Every single time you flip a switch in your house, there is this massive, silent, mathematical symphony happening behind the scenes just to make sure that light turns on instantly. Welcome to this explainer. Today, we're demystifying the power grid, diving into the fascinating physics and the math hidden right above our heads in those electrical lines. We're going to decode that symphony and see exactly how engineers model the journey of electricity.
Think about it for a second. How do engineers actually guarantee that power arrives safely over hundreds or even thousands of miles? It's not just about stringing up some thick copper wire and hoping for the best. As electricity travels, it is constantly interacting with the physical environment. We're talking about resistance, inductance, and capacitance. If we miscalculate these invisible forces, well, systems fail, blackouts happen, and our infrastructure literally crumbles.
Okay, let's dive into this. Here is our roadmap for the trip. First, classifying our power grid. Second, short lines and keeping things simple. Third, medium lines and the capacitance complication. Fourth, long lines and the rigorous reality. And finally, number 5, the universal ABCD constants.
All right, Section 1, classifying our power grid and mapping the journey.
Think of this just like planning a road trip. Our mathematical map scales up in complexity based entirely on distance. We classify transmission lines into 3 distinct categories: short lines, medium lines, and long lines. Obviously, you wouldn't use the same exact planning for a quick drive to the local grocery store as you would for a massive cross-country expedition, right? Well, similarly, electrical engineers have to use entirely different mathematical models depending on exactly how far the power has to travel.
So let's look at the shortest trip first. Section 2, short lines, keeping it simple.
What's really interesting here is how beautifully straightforward the model is for these short distances. In a short transmission line, which is usually considered to be under about 50 miles long, the variables are totally minimal. We really just account for the physical resistance of the wire, which is labeled as R, and the inductive reactance, labeled as XL. They're just lumped together in series. The phasor diagram then neatly maps out the relationship between the sending voltage and receiving voltage. Because the distance is so short, we don't even have to worry about the electrical charge interacting with the ground. It's just a quick, mathematically clean trip right down the street. But as that distance grows, the environment actually starts pushing back. Moving on to Section 3. Medium lines, and the capacitance complication.
Let's see how this builds when we travel, say, between 50 and 150 miles. Notice how this physical wiring diagram suddenly has this new vertical path branching downward? That is labeled C, for capacitance. Over these medium distances, the transmission line and the Earth itself actually start acting like a giant capacitor, literally storing electrical charge. If engineers ignore this, their calculations will be dangerously wrong. You can see how this single physical addition of capacitance drastically alters the vector mathematics, creating entirely new geometric angles and charging currents that absolutely must be accounted for.
Now, simply lumping all that capacitance at the very end of the line isn't always the most accurate representation of reality. So engineers developed 2 much more precise ways to solve this. First, we have the nominal T method, where capacitance is theoretically concentrated right in the middle of the line. And second, the nominal pi method, where it's split perfectly at both ends. We're going to visually compare these 2 mental maps to see how engineers brilliantly tackle the exact same problem from 2 different angles.
First up is the nominal T method. If you look closely at the center of the circuit diagram, you'll see a very distinct T shape formed by the components. Basically, engineers have mathematically split the resistance and inductance right in half. You'll see them labeled as R over 2 and XL over 2, and they've placed the total capacitance right in the dead center. That forms the vertical stem of the T. It's just an incredibly clear, abstract representation that helps perfectly balance the line for their analysis.
And this brilliantly illustrates the alternative, the nominal pi method. Notice how the visual shape has totally shifted? Instead of splitting the resistance and inductance, they're kept whole across the top wire. But we split the capacitance in half, labeled as C over 2, and place it at both the sending and receiving ends. The physical layout actually directly mirrors the Greek letter pi. It's a fantastic little trick for engineers to remember it on the fly. Ultimately, it's just a slightly different mathematical approach to taming that exact same capacitance complication over medium distances.
Okay, but what happens when we are transmitting power across entire states? Just to give you an idea of the massive scale we're dealing with, the North American power grid alone has over 600,000 miles of transmission lines. To put that into perspective, that's enough wire to wrap around the entire Earth almost 25 times. It's time for the true cross-country road trip. Section 4, long lines and the rigorous reality.
When a transmission line spans hundreds of miles, all those mathematical shortcuts we just talked about, they completely stop working. Focus in on that tiny segment labeled dx. Over massive distances, you absolutely cannot just lump resistance or capacitance into the middle or the ends. The real world simply doesn't work that way. Instead, these parameters are distributed uniformly along the entire length of the wire, piece by tiny piece. To figure out the voltage and current, engineers actually have to isolate an infinitely small section, this dx, and analyze its exact microscopic properties.
Which brings us to the rigorous method. Now, please do not panic at the intense math here. We are definitely not solving these formulas today. But I really want you to appreciate the sheer, rigorous reality required to keep the power flowing. Those equations for voltage and current at the bottom incorporate complex hyperbolic sine and cosine functions. Over vast distances, power waves behave almost like high-frequency telecommunication signals. And honestly, these intense, complex formulas are the absolute only way to accurately model that wild behavior.
So why does all this intense rigor actually matter to you? Well, because these exact hyperbolic formulas are what ensure your home electronics don't fry from unexpected power surges. They accurately predict energy loss and transmission efficiency over hundreds of miles. That stabilizes the grid and, believe it or not, keeps your power bills predictable. This is extreme, highly theoretical math, but it has a very practical daily impact on your life.
With all these wildly different methods, how on earth do engineers actually talk to each other to connect these grids together? Section 5. The universal A, B, C, D constants. Basically, we need a universal translator.
And that's exactly what they use. The generalized constants, known simply as A, B, C, and D. Think of this as a universal mathematical framework. It's used to estimate voltage regulation and power efficiency for basically any network, completely regardless of its length or its configuration. So instead of worrying about which specific internal model was used on a certain stretch of line, engineers can just plug the final network values into these four constants to evaluate how the overall transmission line is going to perform from end to end.
Now, the truly crucial point here is this elegant mathematical balance. A times D minus B times C equals exactly 1. It is amazing. No matter how wildly complicated the internal network gets, whether it's a short 10-mile line or a rigorous 400-mile stretch governed by those crazy hyperbolic parameters, if it is a standard transmission network, these constants will always balance out so that AD minus BC equals exactly 1. It elegantly wraps up all those physical complexities, the capacitance, and the distributed parameters we just explored into one incredibly neat, standardized, unified rule.
Which leaves us looking toward tomorrow. As we rapidly shift to renewable energy, we're building massive new grids. Grids that don't just cross states, but span entire continents to connect remote solar and wind farms to booming cities. So how will these rigorous mathematical models and standard constants need to adapt to handle power flowing dynamically in multiple directions across unprecedented distances? It really is the next great frontier in electrical engineering. I hope this explainer gave you a whole new appreciation for the massive, invisible math powering our world every single day. Keep learning, and I'll catch you on the next one.